Chapter 14 is taking a look at fluids. First, section 14.1, fluid density and pressure. So the physics of fluids is the basis of hydraulic engineering, and it applies to a number of different areas of engineering even within that. But hydraulic engineering is one big one. Fluids is pretty critical. And a fluid is any substance that can flow. So that includes water, but also things like air. And any substance that can conform to a container. So this occurs because fluids can't sustain a shearing force, if you remember from chapter 12, where you have a force tangential to the surface. If you push on a fluid tangential to the surface, it's going to collapse in that direction. Fluids can, however, apply a force perpendicular to the fluid surface. So they can push out in all directions. Interestingly, some materials like pitch take a long time to conform to a container, but are still fluids. Now, if you're like me, you might not know off the top of your head what pitch is. I know it more as asphalt, blacktop. And that's a really interesting example of a fluid because it is rigid. Like if you have a chunk of it, you can smash it with a hammer and it shatters, which we'd expect for a solid. But it turns out if you heat it up, it does become more liquid-like, more apparently liquid. And so there's actually the currently longest running experiment of all time is the pitch drop experiment, where someone heated up a beaker of pitch and they put it in this beaker with an opening at the bottom, and they waited to see how long it would take to drop. And they just observed it, right? It's under vacuum, so it's in this isolated environment. And here's the data. So the hot pitch was poured back in 1927. It's been going almost 100 years. So the stem was cut, and then the first drop fell in 1938, right? And then you can see the years in the drops to come, right? They're about every 8 or 9 years. Somewhere in the 90s, the building got air conditioning installed, and so it didn't get as hot in the summer. And then notice the length of time between drops increased greatly because the temperature stayed much more temperate, right? So 12 years, 13 years, right? Where the last one was observed in 2014. So it's probably going to be, it might be until 2027 that we get another drop to fall. But you can check out some YouTube videos of this one as well as some other ones like it. It's pretty wild. This is something that's done. But it's, in short, it's an example of something that appears to be a solid, but is actually a fluid over long enough time periods. You just keep waiting long enough. So the essential identifier is that fluids don't have a crystalline structure. And if you're interested, Veritasium, we've watched a couple of his videos, takes a look at, is glass a liquid? It's a pretty interesting video. I'll leave that for you in case you're interested. So that gives us a little bit about fluids, right? And it's a little bit different than our everyday example. I tend to think of in my everyday that fluids are liquids, right? Whenever I get a cold, my mom was always like, hey, make sure to push the fluids. If I wanted to be really sassy, I could be like, I am, Mom. See all this breathing I'm doing? I'm taking all the fluids in. I don't think that would actually go over very well. So I don't recommend you try that, right? But notice here, our definition of fluids does include gases like air. So that's a slight difference. Now, when we're talking about fluids, we're often going to work less in terms of the mass and more in terms of the density. So the density we would define as the infinitesimal mass in one small segment of it and how much volume that takes up. And so then we can get the density at that particular point. But if we assume the fluid sample is large relative to the atomic dimensions and that has really uniform density, we can simplify our definition to be this lower one. And this is going to be the one that we use in basically every circumstance. Their density is the mass of the object divided by the volume of it. Where we notice it is a scalar quantity, this is not a vector, there's no direction associated with no arrow drawn above it, and the units are that of mass and volume. Kilograms is our units of mass, and then volume in SI units would be cubic meters. So kilograms per cubic meter. And we have some examples of density shown in this table, which are just interesting to see, right? Space is very nearly a perfect vacuum, 10 to the minus 20. The best laboratory vacuum, where we're trying to remove all possible mass, is 10 to the minus 17 kilograms per meters cubed. Our standard air at 20 degrees Celsius, 1 atmosphere pressure, is a density of about 1.21. This is probably the density you'll have to use most often. The other ones that we have are, styrofoam ice is less dense than water, which is why our ice is able to float in our water. And with water, we often will just assume this perfect one of 1,000 kilograms per meter cubed. Seawater, notice, is more dense because of adding the salt. It becomes denser, and that's one of the reasons why it's easier to float in the ocean than in a pool. And then we have whole blood, which is even denser, right? Blood runs thicker than water. It's actually a physics statement. So you can get excited about that. Iron, mercury, the metal, and then we could get into like Earth, right? The different layers of Earth and the sun and stars, and a neutron star is crazy dense, right? 10 to the 18. So that just gives you some range of densities. All right, now another quantity that's going to matter a lot with fluids is pressure. And we could imagine measuring pressure with a little sensor that we put in our gas or in our fluid. And so we drop in this little pressure sensor that is mostly a U-shaped box, but it does have a spring-loaded piston that can move. And so then depending on how much pressure there is in the gas, that's going to compress the piston, right? It's going to push it down. So we can measure that force that acts on the piston over the entire area of the piston, and that will give us a definition of pressure. We're going to call pressure the amount of force that the fluid exerts on the piston, and that it's exerted over that area. So delta F over delta A. So we could look at the limit of this for an infinitesimal force, infinitesimal area, but assuming that the force is uniform over the entire area and that the area is flat, which is what it's going to be for our cases, we can then just write our pressure is equal to our force divided by our area. Now, one thing to note, right? This P looks a lot like our density rho. So I will sometimes write my P to be extra clear with like a little flat line on the bottom and a stem above for pressure. And then for density, I will try to make it extra swoopy for my rho. So if that helps you, you're welcome to use that as well. But the main thing is you want to be able to keep them straight, because I see all too often where students get confused because we will see equations that have both pressure and density. So be forewarned on that. Now, what is this pressure, this force over area? Well, the best illustration I have for this are stiletto heels, right? If someone steps on you while wearing a slipper, you might be irritated, but you won't be particularly bothered. But if someone steps on you with their stiletto heel, you are going to be very much bothered. What's the difference? The person could be the same weight, so they're applying the same force to you, but you really feel that heel. Why? Well, the key is that area, right? The area that the force is being applied on the heel is tiny. So if we shrink our denominator to a really small amount, what changes to in our pressure? Our pressure is going to be way higher. Same force, but smaller area means a larger pressure. So that's what you can think of with pressure versus the slipper. has a huge amount of area, and so the force is spread out. There's less pressure acting on you. All right. Now we could find by experiment that assuming our fluid is at rest, not moving, the pressure will be the same throughout. Like it doesn't matter how that little sensor is oriented in there. So pressure is a scalar. Even though force is not a scalar and pressure is equal to force over area, it's just dealing with the magnitude of the force. So our units of pressure are known as pascals, and they're equal to, the pascal is equal to the unit of force over area, Newton per meter squared. So that's by definition called a pascal, PA. Other units of pressure that appear quite often are the atmosphere, and that's defined to our basic, like if you step outside, that's 1 atmosphere. And so in every problem, if it doesn't mention that you're somewhere weird or at a weird pressure, you can assume by default that there is a pressure of 1 atmosphere. That's sort of the standard. So that's a nice little problem solving tip there. Notice 1 atmosphere is not our SI unit. Our SI unit is the pascal. So we often will need to convert to the pascal in order to get there. And so that's where this conversion factor is helpful, that 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. A couple of other units that are used, torr is a more historic unit. It's based upon millimeters of mercury that happen for measuring devices for pressure. And then we even have pounds per square inch, more commonly referred to as PSI. This is what you know for like your car tire pressure, right? And it's like, oh yeah, it should be about 30 PSI. That PSI is pounds per square inch, and there are 14.7 pounds per square inch in 1 atmosphere. So these are all conversion factors that you can use to go back and forth between the different pressures. So hopefully that gives you some idea. This has now introduced the ideas of density and pressure. We'll wrap up right there.